Hey stranger, I'm the Dredgerist, and in this video series I'll be talking about the game Wipeout from the mid-90s. We'll be taking a look at the game's original source code, and I'll show you my approach to making it run on modern systems. By the end, we will have a version of the game which supports much higher resolutions than the original, runs at much higher frame rates, and contains some quality of life improvements like a new audio engine, whilst trying to keep the spirit of the original game intact. I want to stress that this is not a tutorial on good coding practices. Quite on the contrary, I'll be going through the code as quickly as I can and hacking away at it to get a working build of the game. In my opinion, it's better to get a project like this working first, and only clean it up afterward once you have a good grasp of which code does what and which parts can be removed entirely or should be rewritten. I should also mention at this point, this is a project I'm doing just for the sake of fun and curiosity as a fan of the original game. I own none of the original code or assets, so Sony, if you're watching this, please don't sue me. I also will not be releasing the finished version, but I will try to explain what I'm doing in enough detail that after watching this, anyone with C programming experience should be able to replicate my work. Before anyone points out in the comments that other projects with the same aim already exist, namely Wipeout Phantom Edition and Wipeout Rewrite, I'm aware of those, and if your goal is to play the game on a modern system, you should probably grab one of them. Links to those will be in the video description below. I originally intended to add a section discussing the history of the game, but decided against it as this will be plenty long already and the topic has been thoroughly covered by other people. If you're unfamiliar with the game, or just looking to know more about it, I recommend these videos by Slopes Game Room, The Review Den, Kim Justice, Modern Vintage Gamer, and Noclip. Shout out to them, and again links will be in the video description below. Hopefully you find this as interesting as I did. I learned a lot about the original PlayStation architecture and about the early days of 3D game programming in the 90s. Whenever you hear me complaining about the state of the code, don't get me wrong, I have the utmost respect for the people who made this game, and having worked professionally in game development for quite a while now, I know that things often get messy, that's just how it is. With that out of the way, let's start by taking a look at the leaked source code to get a lay of the land. The source code was released by Forest of Illusion, who have since then unfortunately shut down. The leak contains a single zip archive weighing in at just under 8 megabytes. I will not be sharing the source code for obvious reasons, but I can tell you that it is still available online in places like the Internet Archive. Let's start by unpacking the archive and taking a look at the contents. First up is a folder called API. This contains a bunch of header files relating to a 3D accelerator card library and a Word document explaining its API. It can provide some insight into the capabilities of PC hardware of times past, but it won't be necessary for this project, so we can safely ignore it. Next up is the folder PSX26, which appears to contain some headers from SciQ, a software development kit developed by Psygnosis and SN Systems, which eventually became the official SDK for the PlayStation. Even though we aren't planning on getting this to run on a PlayStation, we'll keep this folder for now, as there's a good likelihood that at least some of the game code is using it. Of note here is a file titled stdio.crap, which simply has a comment stating that it's under construction. Next we have a sound folder, which unsurprisingly contains sound effects from the game. There's also a file called wipeout.fx, which contains a list of the sound files, along with some configuration values, presumably for the game's audio engine. Some sound effects require variable volume, pan, or pitch, and all of them have an integer priority value. Moving on. The next folder is titled Win95, and it contains quite a lot of stuff. There are several folders named after the various developers who worked on the project, containing various bits and pieces of code they wrote. There's also a folder called org src, presumably containing the original source code for the MS-DOS version of the game. Most of these source code files were last edited in 1995 or 1996. The root of the folder is an absolute mess of batch files, executables, DLLs, random files containing source code, as well as images and icons. We might come back to this later just to explore it out of curiosity, but we probably don't really need most or any of this for our purposes. It really looks like the result of several developers working under immense time pressure and without any real versioning control. I love it, 10 out of 10 points. Most of the files here were last edited in 1996, except the make file, which was last changed in 1998. The makefile shows they were using WCC386 as their C compiler, implying that they were building their code with the 32-bit Whatcom C compiler at the time. The second to last folder is called Wipeout PSX, and it looks like it contains exactly what it says on the tin: the source code for the PlayStation version of the game, along with some bits of Windows code for the ATI 3D Rage version of the game. Most of the code was last edited in 1996, with a few files changed in 1998. It's worth mentioning that up until now all the source code has been either C files, along with their respective headers, or straight assembly. Finally, we come to the Wipeout 98 folder, which seems to contain the latest version of the game source. Suddenly the file extensions changed from .c to .cpp, as I'm guessing they changed to a C++ compiler sometime between 1996 and 1998. About a third of the files, consisting mostly of headers, remained untouched since 1995 and 1996, and the other 2/3 were last edited in 1998. This seems like it's most likely our best starting point, so we will focus our efforts here first. The makefile states it's a Microsoft Developer Studio generated nmakefile, format version 4.00, which suggests they were likely using Microsoft's Visual C++ 5 or 6 at this point. To do a quick recap of the files in the source leak, we have a bunch of sounds, some tooling and scripts which were clearly used at some point during development but which we don't need, as well as 3 different copies of the game source. I've compared the 3 versions and found only minor differences, where the Wipeout 98 copy is one where someone actually did some cleanup by removing a few unused variables. Let's get to the fun part now and try to get the game to compile and run. First up, as I don't intend to use an old version of Visual C++, much less the Whatcom C compiler, I will set up a new Visual Studio solution as that's my preferred IDE. I'm setting it up as a new project with existing files and as a Windows app, selecting the Wipeout 98 folder as the project root. The rest of these settings are fine for now, we can always change this stuff later if needed. Let's take a quick look at what we have here. All the source files and headers look like they're in the correct places, and even the resource file containing the icon and some strings was added correctly. Nice. Let's try to compile and see what happens. Well, that's quite a few errors. In fact, there would be more, but the compiler stopped emitting them after a while. I'll try to fix these somewhat categorically, so I'll explain what I'm doing with the first few errors of a certain type, and fast forward through the rest to avoid repeating myself and boring you to death. First of all, we're missing a bunch of includes from the PSX26 and Win95 folders. I could fix this by adding include paths in the project settings, but instead I will just move those folders inside the Wipeout 98 folder, as I would like to end up with a single folder which contains the entire project. I then manually fix all the include paths in the files with errors. Once the includes are fixed, we start going through the rest of the compilation errors. Looks like first up is a definition for time_t, which shows up twice in CoreCRT.h as well as types.h. This conflict is fixed by simply commenting out the definition in types.h. Why that one and not the other one? Because this one is coming from the PlayStation SDK and the other one is part of the Core C runtime, and we certainly don't want to start messing with that one. The next set of errors are due to the compiler not knowing about these assembly instructions. This is happening because I have the project set to compile to a 64-bit target. Switching to a 32-bit target will fix this, and once we have a working 32-bit build, we can try to get it running in 64. We'll probably want to remove all this assembly code anyway, but the priority right now is just to get this to compile at all. Next up, we have some missing type specifiers. Indeed, it seems like at some point in the past this was valid syntax, but modern compilers don't like just saying a type is static. As the error says, C++ does not support default int, but at some point at least C did. We'll fix these by adding the int type. I'll occasionally hit compile, even though I know it's not going to, just to see more new errors as the compilation is still stopping due to too many errors. Okay, so some key names are undefined. We can see above this block an if-def wipeout PC. It's safe to assume we want the PC version and not the PlayStation one, so let's define that. Next up, there are a bunch of errors in winati.cpp. We don't really care about making this run on ancient ATI hardware, so instead of trying to fix it, I'm just going to remove this file. Okay, now the code compiles but does not link. Looks like we're missing symbols for Direct3D 3 and DirectDraw 4. Those are some ancient versions of DirectX, but we'll try adding the missing libraries ddraw.lib and dxguid.lib. Additionally, we have all of these MMIO functions, which are from a Windows multimedia library called winmm.lib, so we'll also add that. Next, we have a missing direct sound library. Let's add that too. It's called dsound.lib. Okay, finally, the code is compiled successfully into an executable, but it just exits immediately. Let's try getting the game to run. We'll quickly try to get this version with Direct3D working if we can, but we won't spend too long on it since we actually want to replace the entire renderer. Let's debug the issue and see what we've got. A variable's uninitialized when enumerating available texture map formats from Direct3D. Let's just initialize these to 0 and see if that fixes it. It does. The game now asks for the CD. This is to be expected as we only compile the executable without any assets. I guess it's time to sort that out next. First I will clean up the solution as I'll be changing up some of the output folders soon. Next I'm cleaning up some files in our project folder. These are all leftovers from the original build process which are unused by the new project and at this point are just polluting the folder. With that out of the way, what I like to do is to have a folder called runtime where the game executable will be compiled to and which contains all the required assets. That way, if you want to distribute the finished version, you can just copy or compress this one folder and everything should be included without any temporary files created by the compilation process. Finally, I will copy over the game assets into the runtime folder, which of course you should be taking from a legitimate copy of the game which you own. I'm using the files from the ATI Rage 3D version of the game, but I would expect that the original MS-DOS version would work just as well. Alright, this should do it for the assets. Let's see what it does now when we try to run the game. It's still complaining about the CD being missing. Let's see if we can find where that's coming from by looking for the error in the codebase. Okay, so the error string is in the resource file but not in the code. Let's look for the error code 2002 instead. Looks like it could be coming from 3 places in the win.cpp file, which is the most likely culprit as it contains our application entry point. Yep, there it is. It's trying to load a file. Let's see if that exists. It does, but with a different extension. It's trying to load a 3DF file, but we have SJR files instead. Alright, let's see what happens if we just change the extension in the code. It's still failing. Let's put a breakpoint in the win main function and step through to see what's going on. It's calling this, which is always failing, and setting the path to the root of the C drive. Well, that's not what we want, so let's replace these with just zeros for now. We wanted to load the files from a path relative to the executable folder, so with some luck this will work. Great, it launched, although it's not drawing anything beyond a black screen. And now it crashed because of a frame rate calculation which contains a division by 0. Not optimal, but it's some kind of progress. At this point I could try to keep fixing this further, but instead I think it's time to start setting up our own rendering. I don't really want to deal with this old Direct 3D rendering code, and I want to be able to run this on multiple platforms, so to that end we'll have to get rid of as much Windows and DirectX specific code as possible. Let's first set up our own window. I'll use SDL to deal with the operating system level abstraction, as that will give us support for all the mainstream desktop and mobile platforms. I'll set up a folder for any third-party libraries we'll be using just to keep the project somewhat organized. As mentioned, SDL is the first library we need, so we'll just grab the latest release and put it in the newly created folder. Next, we add the library to the project linker inputs and set up the correct path for the linker to be able to find it. We also need to add a path for the headers to be included, so let's do that as well. Now we'll create a new header in CPP file to handle our SDL window. We'll include the main SDL header here and set up some variables for the window itself as well as an OpenGL context. I'll be using OpenGL to write the new renderer as it's relatively simple and is supported on just about all modern platforms. I could have gone for a lower level API like Vulkan, but the amount of code required even for some basic triangle rendering is orders of magnitude bigger than what we need for OpenGL. We also don't need the extra performance, as this is a game with such simple graphics and a very low polygon count that the overhead from OpenGL will be negligible. We'll also add some variables like our window size and native display resolution, which we'll use later in our renderer. The rest is standard code to initialize and tear down our window through SDL, as well as a function to change the mode between full screen and windowed. I'll also add an option for borderless full screen later on. We'll initialize SDL to give us video, audio, as well as joystick input. The last time I used SDL it was still in version 2, so a few things have been renamed since then. I'll fast forward through most of this as this is not a video on how to use SDL, just refer to the official documentation and examples when in doubt. Once this is done, we'll go ahead and add a call to our init SDL window function in the existing initialize window environment function to replace the Windows API calls which previously created the game window. Finally, I'll add some code to get the window handle just to get this running for now. Later on this can be removed if we want to support something other than Windows. Trying to run the game now, it immediately complains about a missing DLL for SDL. Copying that into our runtime folder should fix it. And there we go. The game now opens a nice widescreen window through SDL. Alright then, next we have to create our own renderer. First, to clean up some of the stuff we don't need. We won't be supporting the Voodoo graphics accelerator, and we will eventually have the flag for full screen coming from the game options instead of a command line argument. We also don't need this new graphics.cpp file, so let's get rid of that. Looking through the code, the first real texture we're trying to load is wiptitle.tim, so let's look at the function that loads it. It's supposedly a 16-bit texture which matches up with a value we've seen before in the code, namely 565. An educated guess here is that the textures contain the color information with 5 bits for blue, 6 bits for red, and 5 bits for green. A lot of the code here is Direct3D specific, so we'll comment that out soon and replace it with an OpenGL equivalent. It appears the title image has a resolution of 320 by 240, which was pretty standard back then. Let's create a new header and CPP file for our GL renderer. To avoid dealing with OpenGL extensions, we're going to use glue, so that's another thing to add to our third-party folder. We'll use the statically linked version, so the library we want is glue32s.lib. As usual, we'll also need to add it to our linker inputs as well as the standard OpenGL32.lib. Now we can start writing our renderer code. I'll define some basic functions to initialize and clean up OpenGL stuff, as well as functions we will call at the beginning and at the end of each frame. While we're here, let's add a function to load a texture into our OpenGL context. We'll use the term surface ID here to refer to the different textures the game uses. Now we can move on to the implementation side of things. I forgot that we need to define glue_static in our preprocessor in order to use the statically linked version, otherwise the glue code will require a DLL file. Whilst rushing through this, I apparently swapped out the header and CPP files for our GL renderer. A quick cut and paste will fix that, and now it looks like the compiler knows about our OpenGL calls. Nice. Some more cleanup of Direct3D code, as the plan is to remove that dependency altogether. And I've just noticed this block here, which will load different textures depending on the game's track number. It has two options for file names, one of which is PCX and the other is SJR. Since I'm using the assets from the ATI version of the game, the files I have are the SJR ones. Luckily we can switch between them easily with another preprocessor definition, so we will define use_ATI as that seems like a pretty safe bet for now. Another reference to 565. This time it says it's a bool in all caps, which in the line above is just typedef to an int. What the hell am I even looking at? Let's just call it true for now. With all that out of the way, we can get back to our function which loads the title screen image. We'll add the include and a call to the new GL renderer function. Don't worry, I'll move that include to the top of the file later. Now let's fill out the loadGL texture function with just standard OpenGL texture loading code. I've added a parameter for texture filtering just in case we want some textures with it and others without. I would probably choose to have nearest as the option for everything to keep the OG PlayStation look, but to get that 3D accelerated look, it will take some classic bilinear filtering. Having this as an option here means we will be able to keep, for instance, UI textures nice and sharp, while the 3D stuff in the game uses bilinear. There, I moved the include to a better location. I hope you're happy. Now we'll set up some boilerplate code to initialize the shaders we need for rendering. We won't be needing anything fancy here, but let's set this up to be able to reuse the function to set up multiple shaders. The original PlayStation was actually quite limited in terms of what it could do graphically. We have polygons in either flat shaded, Urod shaded, or textured flavors, as well as sprites and colored lines. We will only implement whatever the game is using here, so it will likely be a very short list. That said, we need to write some super basic shaders, and since I can't be bothered to write code to load them from files, I'm just going to include them in the code. We'll start with one which just draws textured polygons, which can optionally take vertex colors. The vertex shader just multiplies the vertex position with a matrix and passes the texture coordinate and color through. The fragment shader just reads the texture at the given UV coordinate and multiplies it with the vertex color. This should do for now. To keep track of our shader bindings and their respective vertex arrays and buffers, we'll create a simple struct filled with GL unsigned integers and we'll call it GL bindings. I'm gonna go ahead and guess that we will also need to render untextured colored triangles at some point, so that's also been added to the binding struct. Now we can pass our shaders into our initialization function, and we'll also quickly prepare a method to deal with the shader bindings. I won't explain this too deeply as it's pretty standard OpenGL stuff which you can look up in the official documentation, or just go through the tutorials on learnopengl.com if you're just starting out. As I mentioned before, we will probably need colored triangles as well as the textured ones we're implementing now, so the shader bindings function also has support for that. Finally, we need to create our vertex array object and vertex buffer, so we'll set up this reusable function called initGeometry for that. Before we forget, we also need to initialize the glue library. I'll do it in the same place where we initialize our SDL window because if this fails, the game won't be able to render anything anyway, so we might as well quit. This glue experimental equals gl_true will force glue to load all extension function pointers, even if the driver doesn't explicitly list them. It's basically a hack for legacy systems, and usually not needed, but it won't hurt either, so there it is. When running the game now, clicking the close window button in the top right corner of the window does not work. Let's fix that real quick because it's annoying and will run and exit the game many times during development. To that end, I'll add a boolean which indicates the window should close and we should quit the game. We'll check if it's true at the beginning of every frame. On its own it does nothing though, so we have to add some code to deal with SDL events. We'll call these SDL input.h and .cpp as it will eventually also contain actual input handling for keyboard and joystick input events. We just need one function in here for now to poll for any events from SDL. The only events we handle right now are quit and window close requested, which will set our flag to true, which should result in the game closing. Now we just add a call to our event polling function and test, and it still doesn't close. Why? A quick debugging with a breakpoint shows the polling is never getting called. We forgot to add a call to SDL at the end of each frame to actually update the screen. And it still doesn't work. What the heck? Alright, so it looks like we're getting stuck in this function called process messages. Understandable, the old code is waiting for the old window to be active so it never exits the loop. The fix is simple. As usual, we'll just comment out the whole function. Now the close button finally works. I'm gonna add a define that will allow us to debug textures easily. All it will do is call a function to render a 2D textured quad at the end of our frame. We also need to create that function, so let's do that. It will take in a texture ID and a pointer to vertex data, a few lines of OpenGL code to bind the texture, find our vertex array, find our vertex buffer and upload the vertex data, find the shader program, and finally draw our vertex array. We'll use a triangle fan, so we only need to pass in 4 vertices instead of 6 if we used simple triangles. Now we need to define the vertices, so I will add a constant with vertex data to draw out a 640 by 480 pixel quad. That should be exactly double the texture size and should easily fit in our window. Now we just need a variable to hold the surface ID which we want to debug, and we can add the call to our new rendering function. Let's also update that debug surface ID every time we load a new texture, so for now at least we should see the last texture which was loaded by the game. And as always, nothing works on the first try. We just have a black screen. Why? Yes, of course, we need to pass in a matrix for our shader, otherwise it doesn't know how to transform the vertices into screen space. I'm not going to write out matrix code by hand because it's tedious and error prone. Also, we will need at least one matrix with an orthographic projection for the menus and UI, and one matrix with a perspective projection for the 3D stuff. Time to add another library to do the heavy lifting for us, this time CGLM, which is just a C version of the GLM library. GLM stands for OpenGL Mathematics, by the way, and it does exactly what it sounds like it does. Luckily it's a header-only library, so it's super easy to add. Just copy the folder into our third-party includes folder and we're ready to use it. We'll need an orthographic matrix right now, so let's define that and add a function to update the projection matrix. Values here for the near and far planes are arbitrary. The original PlayStation had no depth buffer anyway, so hopefully the calls to draw stuff are already ordered correctly in the game code. We also need to pass in the matrix to our shader program, so I'll just do it in the update projection function to ensure that the shader always has the most up-to-date matrix. It's still not working though. Let's make sure we're clearing the screen correctly at the beginning of the frame. I'll also disable blending and vertex culling just in case I accidentally define the vertices backward. Still nothing. I forgot to initialize our renderer, let's fix that. Okay, how about now? Still just a black screen. Ugh, time to read through this OpenGL code and find the issue. Oh, I see there's a small typo in our texture coordinate shader binding. Now it'll work. Okay, but seriously though, I made a copy-paste error fairly early on. If you didn't catch it earlier, it's on the screen now, maybe you can see it. The GL create shader call for the fragment shader had the GL vertex shader parameter passed in as I copied this from the block above and forgot to change it. There are actually 2 takeaways from this. The first one is the copy-paste errors are actually super common in programming. They tend to go unnoticed as usually the code you're copying already works, so you won't get a compiler error or warning or anything of the sort. Just weird behavior in code which at a glance appears to be fine. The second is that when writing OpenGL code, it's a good idea to add error checking wherever the API supports it. In this case, checking for GL link status with GL getProgramIV immediately after linking would have pointed me in the right direction. With the parameter fixed, we finally see the Wipeout title logo as we'd hoped. Don't celebrate too quickly though, as the game already crashed, this time while trying to play some audio. We can deal with audio after we get rendering sorted out, so as always we'll comment out this whole method for now. With that working, let's go through the main function one more time and see what else is happening. Not seeing the mouse cursor over the game window is a bit annoying, so we'll comment out this line calling show cursor with false as a parameter and hope that does it. We soon get to this JJS load sprites function, which is trying to load 3 textures called page 12, page 15, and page 17. Let's see if those will load correctly using the code we've already written for the title screen. These seem to be 256 by 256 pixels each, and the error message says they are texture maps, likely containing multiple images per texture. They're getting loaded with surface ID values of 420, 421, and 422. Since we already commented out the Direct3D specific section of the code, we should be able to just load them with our loadgl texture method. There's this interesting loop which iterates over every pixel and does some kind of weird bit shifting operation. Let's ignore that for now and just see what we get when we load it. Okay, the last texture being loaded is the title screen with surface ID 320, so we have to change our debug texture ID to be able to look at the newly added texture pages with our debug code. Well, they load somewhat correctly, but the colors are all messed up and the images are shifted to the right in a somewhat weird looking way. When these are loaded, we first read 55 bytes from the file and then the rest. An educated guess is that the first 55 bytes contain a header with information about the image, but we just want the raw pixel data. Let's comment that out and check again. Sure enough, those 55 bytes were causing the shifting to the right. The colors are still looking quite wrong, so let's take another look at the loading function. That bit shifting seems a bit strange, so let's comment it out and see what effect that has. As expected, the colors are now different, but still very much incorrect. Not to worry, we can easily fix this with some magic. Now you might be wondering, and rightfully so, why does that fix it and how on earth did I know that this was the solution? Let me try to explain by using a calculator. The original code was shifting the pixel value to the right by 8 bits and doing a bitwise OR with the value shifted 8 bits to the left. What this achieves is that it swaps the left half and the right half of the 16-bit value. Another way to think of it would be that if we took the original 16-bit color and split it into 2 bytes, A and B, we are swapping their order to B and A. Why did they do that? I guess that's how Direct3D wanted the data to look, but I don't know for sure. Now let's look at the new code. We have 2 magic values here. 1F and 7FE0. 1F is just the 5 rightmost bits set to 1. 7FE0 is the 10 bits on the left set to 1 and shifted 1 bit to the right. In a 565 RGB texture, the 1F value will mask out the blue color value. The 7FE0 will mask out the red and green values, but only once shifted 1 bit to the left. In the end, what we're doing here is keeping the blue color value as is and shifting the red and green color values 1 bit to the left. I want to say I got to this by looking closely at the rendered images with the wrong colors, or some trial and error, or just by being very clever. In truth, I saw this bit shifting of color values in other places in the code and decided to try it out. I've played the game before, and so I know what these sprites are supposed to look like. These are the weapon icons that show up at the top of the screen to indicate which weapon you currently have. The rightmost icon is the shield icon, and it should just be in white with a black outline instead of this green one. The one to the left of it is the electric bolt, and it should be blue, also with a black instead of green outline. We could guess from this that the blue value is already correct, and we just need to fix the red and green ones, and that's what the new code does. Now that that works, let's also quickly take a look at the other 2 texture pages we just loaded. 421 contains the game font in 2 sizes, both in white, as well as the graphics for the speedometer and a few assorted UI icons. 422 contains more UI stuff and the fonts again, this time in yellow. Let's disable our debug rendering for now and try to get the text rendering working. We have the center text function, which should be drawing the words press enter on the screen. The function does some math to figure out the coordinates for the middle of the screen, and at the end it calls add prim, which would presumably add the needed sprite for each character of text to the OT. OT here stands for ordering table, and it's a core part of how the PlayStation rendering works. Since there's no depth buffer, you have to order the sprites from back to front to ensure the stuff closest to the camera are drawn last. Long story short, the ordering table is what handles that. We'll add an extra method here, which will set up the vertices we need to draw these sprites in our OpenGL renderer. The game is using this struct called SPRT already, so we'll reuse it. A quick look inside reveals that it contains pretty much what would be expected: the sprite's width and height, the X and Y coordinates, as well as the texture UV coordinates. We need to convert these to some vertices our renderer can draw, so let's do that. Now back to the main menu loop. In the loop, we will add a call to set render begin, which will clear our screen. Then we will define the vertices for the title image and draw that, followed by a call to the center text function to draw the press enter text. Finally, we call set render end to swap our buffer and actually put what we drew on the screen. Well, that's blinking a lot. Looks like it's only drawing it every other frame or so. Also, we have no text. We're calling swap at the end of this loop, so I suppose we can get rid of the set render end call. Now it draws nothing. Let's look at the swap function to see what it's actually doing. We call draw OTag, which is again referring to the ordering table. Previously this would draw everything in the ordering table, so it's calling set render begin, which is clearing our frame buffer. Let's comment out all this old rendering code except the call to set render end, and now our title screen is being drawn without the blinking. We are still missing our text though. Before we look at the text handling code again, let's add some more helper functions to our renderer. We will want control over which draw calls write and read to the depth buffer, as well as blending and triangle backface culling. We'll fill these out with standard OpenGL calls, and when blending is enabled, we'll ensure we have our blend function set to the classic source alpha 1 - source alpha. Now we can add these calls to the main menu loop, as we don't care about blending or depth testing here. We'll also add them to the text rendering function to make sure our text isn't failing to show up because we have the wrong depth and blending state set. Still no text, and the title image is just a small rectangle in the top left corner of the screen. This is to be expected as we're running in a much higher resolution than the 320 by 240 that the game was originally designed for. To fix the size of the image rendering, we could of course just hardcode the window size into the vertex definition, but let's be a little bit more clever than that. In our SDL window, we will add a function to deal with a change in resolution. This will be called every time the window is resized or changed to full screen and so on. We'll add a couple of float variables to hold the ratio of the current resolution and the original 320 by 240. We'll also add a variable to hold the screen scale. The scale is just the smallest of the two screen ratios. This will allow us to draw quads which fill the screen without stretching and cropping the images. We'll set the initial values of all of these to 1 and add the scaling to our text rendering function. We can also multiply the title screen width and height by the screen ratios to make it full screen. It doesn't work because we forgot to call our refresh SDL window resolution after we initialized SDL and created our window. Now that the title fills the screen, let's figure out why our text isn't showing up. Looks like the center text function is doing some math on the X and Y coordinates for each sprite with this upres value, which we haven't investigated yet. It's currently set to 2, so maybe our text is just going off screen due to it. Let's first make sure we aren't somehow drawing the text behind the title screen by commenting out the title screen draw code. Nope, that's not the issue. Let's try removing the upres calculation from the text sprite's X coordinate and see if that fixes it. It does not. I'm starting to suspect there's something wrong with the newly written sprite rendering code. Well, this ordering for the vertices feels slightly unintuitive, so let's rewrite it in a different order to make sure there's no mistakes here. It occurs to me that we will also need to calculate some kind of offset for the HUD, as the game was designed for a 4:3 screen ratio and most screens now are 16:9, and I'm actually planning on playing this on a 32:9 display. We'll define a couple more floats for our X and Y HUD offsets and calculate them in our refresh SDL window resolution function. Back in our text rendering, let's also get rid of the upres calculation for the Y coordinate and add our HUD offsets to the vertex calculation. Now we finally have the text showing up, and it even looks like it's centered correctly. Unfortunately, it doesn't look very good because it has black borders which are supposed to be transparent. This is also in line with how the original PlayStation handled transparency in sprites. A pure black pixel with all color values set to 0 would not be rendered. It's basically a type of masking where there is no real alpha blending, but you can use a black color to make pixels fully transparent. We can easily simulate this in our renderer by passing a uniform to the shader, which will then check if the color of the current texel is 0, in which case the fragment is discarded. With that, we finally have a pretty good looking title screen and text. At this point we need to deal with what was probably the most frustrating part of this codebase for me, the input handling. There are a lot of variables and a lot of code dealing with all manner of input devices in the code, and a lot of it contains some pretty unintuitive bitwise operations as well. Fun fact, There are a lot of references in the original codebase to something called negcon, which is what I suspect the variable neg1 is also referring to, and that's a kind of weird game controller from Namco where you can twist the controller and that would function as steering. Though I've never tried one of those out, I suspect the whole thing was about as clunky as this input handling code. So in short, what we want to do is change the value of this neg1.bits here, as that will change pad, which in turn changes xpad. There are only two ways out of this main title screen loop. Either we time out and switch to attract mode, or this get menu key function returns something other than 0. We want the latter to occur, so in the get menu key function, we can see the xpad variable is the one being checked. So now we have to figure out how this neg1 variable works, and scrolling up the old main function which contains the title menu loop early on, we see a call to this init controller function. From there, we end up in initPad, which is passing the address of neg1 as the first parameter. Inside initPad, the first parameter is called buff_a, and its value is being set to a variable called etc transfer buffer1. Are you still with me? So ultimately the thing we want to be changing is the value of etc transfer buffer1, which contains the address of neg1, which after some operations ends up affecting the value of xpad, which is what will get us out of the title screen. Nice and simple. Let's write out some code in SDL input to do this, and we will try to handle all the input buttons in one go here. First, we will want to map out the SDL keyboard scan codes to the ones used in the game. I remember there was a list with the game's keyboard mapping in the etcvars.cpp file, where we have this Wipeout PC preprocessor define switching between two sets of mappings. We'll take the PC one and copy it out to our SDL input. Then we replace all the Wipeout scan codes with SDL ones while keeping the exact same order. We'll also leave the comments so we know what each key is supposed to do in the game. Then we add a function to map these keys for us. I won't bother explaining this very deeply, as it's frankly quite boring, and I'm still traumatized by the sheer amount of code related to inputs in this codebase I had to read through to try and make sense of this and all the time it took. Suffice to say, we will map these out, and then we can use them in the poll SDL input function to change the value of etc transfer buffer1. The whole thing is kind of a mess and should be rewritten, but I want to get it working with a minimum of changes to the original codebase first. With that out of the way, pressing enter should actually get us past the screen, and it sort of does. We can now see the main menu text, but the background has not changed because we haven't gotten that far yet. Eventually I might come back to this and add gamepad support also, but this should do for now. Let's move on to more fun things. Right, we should be able to figure out this main menu background pretty easily. Let's quickly look through the code and see where we end up after the title screen. Looks like we go into a function called menu control, which sounds just like what we want. Okay, this method isn't the most readable, but it's not the worst either. Let's take a look at the methods loading textures. We have this call here trying to load what seems like a copyright image. There are two versions here, load image 4 and load image 8, so we'll add a couple of breakpoints to see which branch we're taking. We're calling load image 4. Let's see if we can adjust that to work with our OpenGL renderer. So there are three different versions, only one is active, and it's a blank function containing only a return 1. Fine, less work for me. Next up we call a familiar method, JJS load 16-bit texture, this time with a new texture file just called wipeout1.tim. Okay, so this is the main menu loop. We'll add a call to set render begin at the beginning of it, and look here, it's a commented out method called show menu background with a comment just saying PC wipeout. Not sure why that's commented out, but let's bring that method back and make it do exactly what it says it does. As expected, it contains some code to draw flat textured polygons, presumably with the background image. We'll comment that all out, and add basically the same stuff we did for the title screen. What is this comment here? This is bodged so that we get a single pixel where Steve clips them because I couldn't fix it. Crap, huh? I don't know what that means, but we're about to unbodge this real quick. Alright, what else do we have here in the main menu? These calls to center text also pass in what appears to be a constant for the text color. We don't really have red text in the original PlayStation version of the game, although the ATI version did, and it was hideous. But while we're here, let's add support for this in our sprite rendering function. If you remember from when we loaded the sprites, we had the game font in white and yellow, so presumably the red text constant refers to the yellow version, as in other places in the code we call these text routines with a constant white text. So the red text sets the green color channel to a constant bright red translucent. We can use this in our sprite rendering function to switch between yellow and white. When we want the yellow text, we need to switch the texture surface as well as move the UV coordinate down by half a texture map, so 128 pixels. Let's try out these changes so far. Oh, look at that, the title screen now has yellow text. Nice, and the main menu has a proper background as well. Looks like navigation is working, but a few things here are missing. There's supposed to be 3D models spinning under this text, and when you try to quit the game, you can't even see the options for yes and no. Back in the main menu code, we have a call to a function named callMenuSelector, which in turn calls display buttons, which once again contains some code to draw some textured triangles. We'll replace it with our own code to see if we can get the button sprites to show up in the main menu. A quick test shows absolutely no change. We'll get back to this. For now, let's set a breakpoint and debug the main menu code to see what's actually happening in there. We have some kind of function pointer which is getting called and takes us into the draw main menu function. In there, we call draw team ships, which should be drawing a 3D model of one of the vehicles from the game. That calls this transform static menu object, which contains the actual code to draw an object as it's called in this code base. This rendering code will iterate over each primitive in the object, meaning triangles, quads, etc., of the various different flavors supported by a PlayStation. In the same object.cpp file, we have some similar looking functions titled transform static object bodge and transform static object. At the moment, I don't actually care about the differences in the menu version, the bodge version, and the regular transform static object. They should all be doing pretty much the same thing, so let's try to get one version of this code that works for all cases and just always call that instead. We'll comment out the entire transform static menu object and just have it call the regular transform static object, which we will also comment out and replace the contents with our own rendering code. We will start with the usual code to set up the depth and blend states in our renderer, but this time actually writing and reading to the depth buffer. At this stage we have to check if the camera pointer actually contains something, as in the main menu rendering code it does not. In that case we need to get a rendering matrix from the object itself, which contains a struct called skeleton, which is acting as a kind of transform hierarchy. We will need to add methods to deal with these matrices in our renderer, but first the other branch. In the case where we do have a camera, we will get the object's model matrix as well as the camera matrix and pass those into our renderer. Back in our GL renderer, we will add support for rendering 3D stuff. For that, we will need to set up a projection matrix with a perspective projection. The values I'm using here for the near and far planes are somewhat arbitrary, but I settled on these after a bunch of trial and error whilst debugging the code and seeing what sort of values the in-game matrices were holding. Next, we will declare a set of functions to deal with all the values coming from the game code. We need to be able to set a model matrix, a view matrix, to reset those matrices to the identity matrix, and to be able to translate them in 3D space. We will also add a function that takes the current camera position. Now we can add the implementations for these functions, but we need some helper code to convert values from the game into something we can actually use. The reason we need to convert stuff here is because the original PlayStation did not have a dedicated floating point unit in its CPU, meaning there are no floating point values and everything is done with integer math. I guess that made sense when you only had 2 MB of RAM and were only rendering in the low resolution supported by classic blurry television sets, but even then the graphics tended to look a bit wobbly as they snapped to integer pixel values. We'll add a define called toGLFloat, which converts any integer values we pass in to a GL float and divides the value by a floating point value of 4096. This may seem like another arbitrary number, but let me try to explain why I chose this specific value. When you work exclusively with integer values, you obviously don't have the accuracy of floating point values because you can't represent fractions, but you can do the next best thing, which is to use something called fixed point arithmetic. The basic idea is that before a division or multiplication between values a and b, you first multiply them both by another value, for example 10, then perform your division or multiplication, and at the end divide the result by 100 to bring it back to the original scale. So instead of a times b, you have a times 10 times b times 10 divided by 10 times 10. The end result is more accurate than just doing the division or multiplication with the original values directly, because it gives you the ability to do maths with fractions which you could not represent in an integer otherwise. For example, the value 0.5 could not be represented correctly as an integer, but if you multiply it by 10, you get 5, which is a nice integer value you can now do your math with, as long as you remember to divide the result at the end. You don't have to use 10 though. In fact, when writing code for a relatively slow processor, you want to do things which are as fast as possible, so you can just use bit shifts instead, as those are pretty much as quick as any CPU operation gets. So back to the value 4096. Whilst looking over the code, I saw multiple places where two values were multiplied together and the end result was bit shifted to the right by 12. This looks like two values were actually bit shifted left by 6, then multiplied, and the result is shifted to the right by 12 bits to bring it back to the original scaling factor. Therefore, my thinking was that if the game was using 6 bits of accuracy for the arithmetic, and we want to have enough accuracy in our floating point versions of the values used in the game, we should use a value of 1 shifted to the left by 12 bits, which is 4096. I'm not entirely sure about my logic here, nor am I convinced this is the best thing to do, but I think as long as you use the same conversion everywhere including all the 3D vertices, matrices, and camera positions, it should work out. This also didn't produce any visual artifacts as far as I could see, so it works for me. Okay, with that out of the way, let's deal with these matrices. The matrices in the game are 3x3 in size as they only contain rotations, with the translation coming from a separate 3-component vector, so we can quickly convert all the values and store them in a 4x4 matrix, which CGLM as well as our vertex shader can use. We do the exact same thing with the model and view matrices, and finally the camera position, which we also convert and store in our own 3-component vector variable. Next, we'll copy over the source code for our 2D fragment shader and set up a new 3D shader for it. Even though the code is exactly the same for now, we want to use a separate shader program because we can then make changes in our 3D pipeline without touching the 2D stuff. We'll add variables in our GL binding struct for the new shader and then add the calls to initialize them. To finish up, we need a function to multiply our newly created model, view, and projection matrices together into a single MVP matrix, which we then pass into our 3D shader program. Last but not least, we need to add a couple of functions to draw 3D triangles and quads. These look just like our 2D drawing function, but of course, use the new 3D shader program instead of the 2D one. The triangle rendering function just draws one individual textured triangle, whilst the quad rendering function draws two textured triangles at once in a triangle fan configuration. Now we can finally fill up the transform static object function with the code to use all of these new 3D rendering functions. After they're set up, we still need a function to actually deal with all the different data types the game might try to draw. We'll create a new function for that and start with type GT3, which stands for Gouraud Shaded Textured Triangle. Here we need some more helpers to convert the game's integer values into floating point ones our renderer can use. We'll add a definition called toGLVert, which takes a vertex from the game and calls to GLFloat on all three components x, y, and z. Then we add another define, this time called toGLUV, which just converts UV coordinates from an integer range of 0 to 255 into a floating point range of 0 to 1. Finally, we add one more helper called toGLRGBCol, which will convert 7-bit color values from the range 0 to 127, again into floating point values of 0 to 1. Now we can convert all the polygon data into data our renderer can use. But there's one more thing before we can run this. We need to figure out how to bind the correct texture for our draw calls. We'll add a helper function to deal with this, which mainly consists of 2 lookup arrays and some code hacks to make this all work. The table values were derived from debugging the textures as they got loaded in our loadGL texture function and writing down what surface IDs they were being loaded into, then comparing those with what was being used by the various draw calls coming from different parts of the game. This is a super dirty and hacky way to deal with it and really should be rewritten, but as far as I can tell it works. Now we finally have everything needed to draw 3D triangles of the GT3 primitive type. We of course need to support the other types of primitives also, but the code for all of them is pretty much the same, so I will skip typing it all out and just quickly scroll through the end results so you can pause the video if you for some reason need to look at some individual primitive type. Until now we've only implemented textured 3D polygons, but the game does in fact also use untextured colored polygons, so let's quickly add support for those in our renderer as well. There's nothing new here really, it's just a copy of the textured 3D drawing stuff minus the texture and option to discard black pixels. With all that added, we can finally test to see if this all works. It doesn't, because we forgot to add the call to actually render the object with our newly created function. Let's fix that and test again. It still doesn't work, but there are no errors either. Oh, there's a call before the main menu loop to SJR new texture, which we probably want to look at. That branches into 2 different calls, either to SJR load texture BMP menu or SJR load texture BMP. A breakpoint shows we go into the menu one at this point. Inside we find some very familiar texture loading code where all the direct 3D stuff we've already commented out. It even does the same bit shifting magic to each pixel as we had in our sprite loading function. We have not, however, added a call to our texture loading function yet, so let's add that and test. Wow, we have a 3D spinning ship in the menu. The colors are all wrong as the ship is supposed to be green instead of red, and the nose of the ship is missing entirely, but it's getting there. We can even see the other 3D objects when we navigate the menu, as expected. Well, I don't know what's wrong with the colors, but it looks like our untextured polygon rendering isn't working as the front of the ship is missing. We never added code to pass the MVP matrix to that shader program, so let's quickly fix that and take another look. Nice. Now the ship geometry looks good, and we just need to figure out the color situation. Let's have another look at the main menu loading code. We have all these calls to load text model, which is just setting up paths for the model files and calling load PRM. That loads the model and does whatever else it does, and eventually goes into a loop where it looks like it's changing the vertex colors of every primitive with a find nearest color index function, which is stored in the red color channel, and setting green and blue to 0. That would explain why the ship was all red. My best guess is that at some point code was added here to convert the original color values to a lower color depth for hardware which did not have support for fancy 24-bit colors like the original PlayStation. The function name implies some sort of indexed color palette was used instead, but we want all the colors, so let's get rid of this and leave the vertex colors untouched so we can see what was actually in the game assets. Lo and behold, the ship actually looks good now. I mean, it's in front of the main menu text when it's actually supposed to be behind it, but we can fix that later. More importantly, I want to fix the missing text when you try to quit the game. We previously changed the center text function to use our new sprite drawing code, but there are other methods like add text which we have not yet touched. Let's do the same thing here and get rid of the upres value calculation from the x and y coordinates, remove the call to add prim, and replace it all with a call to our render sprite function. The function below is called add number, and we'll preemptively apply the same treatment there. Now we have the actual options for yes and no when trying to quit the game. Great. Now to adjust the menu code so we draw the ship before we draw the text. This block here checks if the current display object exists, so I assume this is drawing the 3D model in the menu. Commenting it out confirms it, as the ship is no longer drawn. Let's grab this chunk of code and move it up higher in the main menu routine to see if we can just change the draw order that way. This works as intended, and quickly going through the different menu options shows there are still a couple of things to fix before we can move on. The display buttons function is not working, so let's take another quick look at that. This vertex code is upside down. The height value should be subtracted from the Y position. Alright, now we see half of the button sprite we expected to see. Looks like the second triangle vertex is still wrong. Yep, sure enough the X coordinate for the top right vertex was incorrect. Another copy and paste error. That's also working now, but the graphics options menu is not showing anything at the moment. I don't expect the actual options to work, but we should at least see the text on the screen. Let's see here. We'll add a breakpoint so we can step through the code while it's running and see if we can spot where this is failing. Add text is being called with a negative Y coordinate value. I'm pretty sure this isn't supposed to be negative 116, so the question is, why is it that? The value is initially set to 140, but I don't see where it's being changed after that. Hold on. This variable is declared as a car. A signed car, that is, which holds values from negative 128 to positive 127. When it's set to 140, it overflows and becomes negative. Let's change it to an unsigned car so it can actually fit the value 140 and run the game again. That looks good to me. I think at this point all of the rendering in the main menu is working well enough, so let's see what actually happens when we try to start a race. Well, I didn't expect it to work, but at least the HUD is already showing up with the lap number and our position in the race. I guess that means the add number function is also working as intended then. Since this video is almost an hour long and this seems like a good place to stop, I'm gonna call it a day here. In the next episode we'll tackle the in-game rendering of the track, the ships, the background, along with any other in-game graphics. If you stuck around this long, I have to assume you either fell asleep or actually found this somewhat interesting. If so, consider subscribing and leaving a like or a comment, as it would help these videos get more visibility and I would love to grow this channel. With that, I say thank you for joining me and I hope to see you on the next one. Later.